welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aryabhatta College, University of Delhi. So in the previous lecture we started with a new module which is Fibonacci heaps, and we looked into the various introductory details of those Fibonacci heaps. So here today we will take quick recap of these Fibonacci heaps, and then we will be looking into the more structural details of these heaps, and then we will be covering some of the operations. So this is going to be the agenda for our today's lecture. So let me give you a quick recall of these Fibonacci heaps. So Fibonacci heaps basically a collection of min heap ordered rooted trees in which every tree is going to obey that min heap property, according to which the key of a node is greater than or equals to the key of its parent, and the implementation of these Fibonacci heaps is going to take place with the help of a circular doubly linked list. So if we look into a quick kind of site on this, the structure of the Fibonacci heap, which we obviously discussed in our previous lecture. So here we have 5 min heap order trees, one, and all these min heap order trees are kind of we can say linked with a circular doubly linked list as shown in this figure. So all the roots, which is 23, 7, 3, 17 and 24, are linked with the help of doubly linked list. So if you can see here, one link is going in the right direction and another link is going into the left direction, and these are closed in a way that these are in the form of circles. So one, they are the doubly linked list, and another one they says that they are the circular doubly linked list. And similar status is with the children of the tree having 3 as its root node, which are 18, 52 and 38. Then we have 26 and 46 as the children of the tree having 24 as its root, and so as we have 30 with 17 as its root, and there is a pointer which is H min, which is pointing towards the minimum key in the this heap, and because of this min heap ordered property, your minimum key is going to be found into the root node list only. So that is what we have already seen in brief manner. So when we talk about the implementation strategy, I have told you that there is going to be circular doubly linked list. Now this circular doubly linked list is having 2 advantages as far as Fibonacci heaps are concerned. So first is we can insert a node in any location or remove a node from anywhere in a circular doubly linked list in order one time, and second, given 2 such lists, when there is a concatenation is required, if we want to concatenate them, or if in case of that concatenation into one circular doubly linked list, that is also going to be that is also going to take place in order one time. Now when we look into the node structure, each node apart from its usual attributes, each node is having 2 kind of we can say extra attributes. One is known as the degree of the node, and another one is to show that whether the node has been marked or not. So first of all, let us try to understand the term degree. So degree is actually the number of children in the child list of node x will be the degree of x, whatever will be the number of children in the child list of that node, that is going to be the degree. And next the attribute is x dot mark, which is a Boolean value attribute. Now this Boolean value attribute indicates that this x node, whether this x node has lost a child since the last time x was made the child of another node. So since starting the time this x was made the child of another node, has x has lost child or whether node X has lost a child, yes or no, that is going to be shown with the help of this Boolean valued attribute, which is X dot mark. And here how this is relevant or what is the significance of this X dot mark, that we will be covering in our various operations and obviously the amortized analysis. All the newly created nodes when we start the building of heap are actually unmarked, and the node X becomes the unmarked whenever it is make the child of another node. Now, how someone is going to access the Fibonacci heap H, that is through the H min pointer, which is H dot min, and this is a pointer which is pointing towards the root of the tree containing the minimum key, and we call this node the minimum node of that Fibonacci heap. And this H dot min we have already seen in this figure or in our previous figure. So, here H dot min is actually pointing towards the node 3, which is the minimum key. So, H dot min is kind of an we can say entry point to this Fibonacci heap, or we can say access the Fibonacci heap using this H dot min. And if more than one root has a key with that minimum value, because there can be duplicate values, then any such root may serve as the minimum node. So, there is no kind of kind of a we can say controversy or a discrepancy in case of two such nodes. But whenever a Fibonacci heap is empty, your H dot min is nil. So, this is the condition when your Fibonacci heap has just started kind of just started to be grown, or we can say till that point when we say create a Fibonacci heap. So, that is a heap without any key. That time the value of H min is nil, because Fibonacci heap is not having any of the trees. So, this was actually regarding the structure. As far as roots of all the trees are concerned, we have already seen that these are linked together using their left and right pointers into a circularly doubly linked list, and this linked is through which the roots of all trees are connected to each other is known as the root list of the Fibonacci heap, and the pointer H dot min will point to the node of this root list whose key is minimum. And within this root list, your tree may appear in any order, or your tree may appear in any specific order. That is not a kind of we can say hard and fast decision to be implemented. But the point which we need to be taken care which we need to take care is about your H dot min. Now, in our previous lecture we talked about that there are some mergeable heap operations. Most of them are relatively taking lesser time as far as amortized time complexity calculation is concerned, if we talk about Fibonacci heap as compared to other binary heaps or so. So, there are some mergeable heap operations, and these mergeable heap operations on Fibonacci heaps, they delay work as long as possible, they defer the work. Now, what is the example of deferring the work that we will be taking when we will be looking into these procedures? What procedures I am talking about? So, we have a procedure of make heap, we have a procedure insert, then we have a procedure minimum, extract min, union, decrease key and delete. And what is the we can say what is the meaning or what is the gist of these procedures, that is also kind of being covered in our last lecture. Here what are we going to cover in terms of procedure is how these procedures are going to take place in case of your Fibonacci heap. So, normally when we study any new data structure, we look into the various operations of that data structure and also analyze the performance of those operations. So that is kind of a normal requirement if we study these kinds of core and theoretical computer science papers which are related to data structures, algorithms, or maybe advanced data structures and algorithms. This is a very important step to analyze the performance of all the operations. So here now onwards we will be looking into one operation and we also analyze it. Now as far as analysis is concerned, I have told you in my first lecture about Fibonacci heaps that the analysis here is going to be amortized analysis. Now let me help you in recalling that amortized analysis is kind of having some expensive operations which are not very frequent and having some other non expensive operations which are frequent, and then averaging out the total complexity for all these for this sequence of operations is about the whole study of amortized analysis. Now amortized analysis can be done with the help of three methods. One is aggregate method in which we apply a different kind of strategy. Then we have a potential method, and apart from that we have a method in which we work with different credits also. So here we are going to work with the help of potential method. We will be not applying other two methods. So here for a given Fibonacci heap H, we are going to take the two variables. One is T dot H, another one is M dot H. So T dot H indicates the number of trees in the root list of H, and the example which we have seen till this point is having 5 trees in this root list. So T dot H for that particular example is equals to 5, and as far as we talk about M dot H, so M as in marked nodes, M dot H is the number of marked nodes in this H. So if you can see here is a figure in which I have taken that previous example of a Fibonacci heap. So total number of trees in this Fibonacci heap is 5 and the number of marked nodes is 3. So marked nodes are 18, 39 and 26 as you can see on the screen. So with the help of these two terms, one is T dot H, another one is M of H or M dot H if we can say. So we need to define our potential function for the purpose of amortized analysis, and this potential function is denoted by theta h as you can see on the screen, and this theta h is defined as T of H plus 2 of M H. So whatever is the number of trees in the root list of this heap H plus 2 multiplied by the number of marked nodes. So if we look into this example, the potential of this Fibonacci heap is going to be 11, which is 5 plus 2 dot 3. So 5 is number of trees and twice into the number of marked nodes. So the number of marked nodes is 3. So 5 into 2 dot 3 is going to be 11. So the potential of a set of Fibonacci heap is the sum of the potential of its constituent Fibonacci heaps. So there can be various Fibonacci heaps within one. So we need to sum up for calculating the potential of the overall Fibonacci heaps. So why I have told you this potential function here, because soon we will be going to start with the operations of these Fibonacci heaps, and then we will be looking for or we will be requiring this potential function, its meaning and its definition, in order to analyze the operations in an amortized way. So when we talk about Fibonacci heap, so Fibonacci heap application begins with kind of no heaps, no trees. So the initial potential therefore is going to be 0 because it is not having any trees and neither it is having any marked nodes. So potential, if you are able to recall that is required to be non-negative at all the subsequent times, and the initial potential is 0 because Fibonacci heap is not having any heap, any tree inside this. Also, when we talk about the upper bound on the total amortized cost, that will be provided by on the upper bound on the total actual cost for the sequence of operation. Now, this is actually, we can say, a standard statement as far as amortized analysis is concerned, that the upper bound on the total amortized cost provides an upper bound on the total actual cost for the sequence of operations. So, with this kind of background of the potential function, which is denoted by phi h equals to T of h plus 2 into m of h, we have seen marked node, we have seen root, the list thing. Let us look into the various operations of mergeable heaps, or various operations which are also valid in kind of Fibonacci heap, that we will see, and then we will be moving on to the different decrease key and delete operations which are not part of mergeable heap operations, but yes, Fibonacci heap supports them. So, first is about creation of a new Fibonacci heap, and in order to make an empty Fibonacci heap, the procedure which we are going to call is the make fib heap procedure. This make fib heap procedure returns the Fibonacci heap object h, where h dot n is equals to 0, n is the number of trees in h. Presently, we have just created the Fibonacci heap, we have not inserted any nodes. So, h dot n equals to 0 and h dot min obviously equals to nil, because we do not have any kind of we can say element, as there are no trees in h. So, this is just kind of a very simple function in which we are just creating a Fibonacci heap which is essentially empty. So, here if we can look from the point of view of the potential function thing, T of h is equals to 0 and also m of h is equals to 0, because there are no trees, there are no marked nodes as such. So, the potential of the empty Fibonacci heap which is denoted by phi of h is equals to 0, and the amortized cost of make Fibonacci heap is thus equals to its actual cost, which is nothing but order 1. So, if you can look into the comparison table of the analysis of operations of your what we call Fibonacci heap and binary heap, you can refer to the first lecture of this Fibonacci heap, and then you will find that the amortized cost of make fib heap is equals to its actual cost, and this is nothing but order 1. With this, let us move to the next operation, which is about inserting a node. So, while inserting a node, we will be kind of we can say we will be having two parameters in this insert a node function. One is the heap or the Fibonacci heap in which you want to insert that node, and second is the kind of node x. With in this insertion, the assumption is that node has already been allocated and x dot key has already been filled in, and then we will be writing a procedure to insert a node x into a Fibonacci heap h. Now, what is that procedure? So, here is a pseudocode to that procedure which says fib heap insert, and the parameters which we are passing is h, the heap heap pointer, and next is the x, which is the node to be inserted. X dot degree is equals to 0, because presently it is not having any children and degree represents the number of children. So, x dot degree is equals to 0. X dot p, which is the parent, presently we have not attached it to any of the trees. If available, then only we will be able to say that parent is equals to nil. So, x dot p is equals to nil. No children of course, so x dot child is equals to nil. x dot mark is equals to false because the node has not been marked yet. So, x dot mark is equals to false, and if h dot min equals to nil, then we need to create a root list for h containing just x. So, h dot min equals to nil means that you do not have anything or any tree within that Fibonacci heap, and because h dot min handle is nil. So, h dot min now will point towards the x because that is the only element available now, because that is the only element now available with your Fibonacci heap. Or if it is already being created, that means heap is already there in existence, we can insert x into the root list of h, and if the existing minimum key is greater than the key of x, then we need to assign h dot min as x, because that is now the key which is minimum. If it is not like this, then there is no need to disturb the h min pointer. And finally, as we have kind of incremented one more element or one more tree into it, so we will be saying the number of nodes in this h, which is h dot n, is equals to h dot n plus 1. That means we are actually kind of incrementing the total number of nodes here when we have inserted a new node containing x. So, here is a figure. The earlier figure or the figure on the above on the screen above is having 5 trees, min heap order trees, with root nodes as 23, 7, 3, 17 and 24. And if we want to insert one more particular node, which is nothing but 21. So, 21 is inserted after 23 and 7, and why this is so? Because I have already told you that there can be no specific order in which these elements are to be stored. But here, if my h min is already on the point is already on the key 3, which is lesser than the newly node key of the newly inserted node, no point in disturbing h dot min. If it would have been 2 in place of 21 or 1 in place of 21, then this h min also has to be kind of would require to be updated. But presently 3 was the minimum element in the root list, and 3 is still the minimum in the root list because we have inserted an element which is greater than this 3, and that element is 21. So, we are not going to update h dot min. Then moving further, if we talk about the amortized cost of this fib heap insert, amortized cost, as I have told you, that we will be using the potential function for this amortized analysis, potential method, and the potential method works on the basis of potential. So, potential, as I have told you, that it was kind of it is denoted by T of h, and that T of h is equals to number of trees in this heap plus 2 into number of marked nodes, and the example to this we have already seen. Now, in order to determine the amortized cost of fib heap insert, let us say that h be the input Fibonacci heap and h dash is the resultant Fibonacci heap. So, h is the heap which is given on top of the screen, and h dash is the resultant heap which is created or which is being obtained after addition of this newly inserted node, which is 21 here. So, T of h dash, if we look, is equals to T of h plus 1, and m of h dash is equals to m of h. What does it mean? This essentially says the number of trees in the Fibonacci heap h is equals to the previous number plus 1. So, for newly heap H dash, it is going to be T of H plus 1, the previous plus 1, because we have inserted a new node into it, and M of H dash is equals to M of H. That means the there is no difference between the marked nodes, because we have just we can say inserted a node, and we have not we have not gone into the nuances of this marking thing and marking thing as of now. So, the potential is going to be increased by 1 definitely, even if it is an empty heap. The earlier potential is 0, and now the newer potential after adding 1 element is going to be 1. So, that is also an increase of 1. So, if we can say T of H plus 1 plus 2 of MH minus T of H plus 2 of MH is equals to 1, because there that is the only difference in number of trees attached. And since the actual cost is order 1, the amortized cost, if you can see, is order 1 plus 1, which is essentially again order 1. So, here for this fib heap insert, there is no difference between the actual cost and the amortized cost. Now, if we let us say want to find the minimum node. So, minimum node is actually we can say is tied up with the handle h dot min, or minimum node of a Fibonacci heap is simply given by the pointer h dot min, and we can find it, or we can kind of retrieve it in order 1 actual time. Potential here is actually not changing at all. So, no change in the potential. So, amortized cost is equals to the actual cost, which is order 1. So, here if you can see in this lecture, we started with a detailed drill down into the structure and looking into why we are implementing this Fibonacci heap with the help of circular linked list. Then we started with the operations, and we have looked into 3 of its operations, which is make creation of an empty heap, then insertion of a node, and then finding the minimum node. We have also analyzed these operations with using the glass of the amortized analysis thing, and the method which we have opted here is the potential function method. So, this is what we have covered in the lecture till now. Here is a list of references which is being used for the preparation of lecture. More about the leftover operations of these Fibonacci heaps in the upcoming lecture. Till then, take care. Goodbye.